Okay, so last time we studied proof by contraposition, and also we studied the proof by contradiction. So in the case of proof of contradiction, we basically assume that the conclusion is false and deduce that cannot be true. So like for example, we would like to show that a proposition P is true. In this case, we assume that P is false and conclude that both R and negation of R are true for some proposition R, which definitely cannot happen. So, so that we can deduce that P is true. And one example of this proof by contradiction was we can show that square root of 2 is an irrational number, and proof was done like this. So we assume that not P is true, meaning that square root of 2 is rational. So from the definition of rational numbers, there exist two integers A and B, such that square root of 2 is A over, represented by A over B. And we can also make an additional assumption that GCD of A and B is equal to 1, meaning that A and B have no common factors. So here, R is the proposition that A and B have no common factors. But from this equation, we obtain this, or equivalently obtain this equation by squaring this equation, meaning that A squared is an even integer because there's a two factor here. So A is an even integer, so A is equal to 2 times m for some integer m. And we plug in this equation into the previous one, and we obtain another equation which has exactly the same form as the previous one. So we repeat the same argument to conclude that B is again an even number. So we know here A and B are both even integers, so that they definitely have the same common factor too. So this proposition R is false. So R is true, and the negation of R is also true. So, so we can conclude that the first assumption is false, meaning that the original statement, proposition P is true. And let me show you another example. So this is one of the very popular problems in combinatorics. It's called tiling. So here's we are given some regular checkerboard, but this checkerboard is non-regular because this both upper left and lower right squares are removed. So in general, we should have 8 times 8 in total 64 tiles, but 2 of them are removed. So we now have 62 tiles. And the question is, can we tile this board? So the question is that can you fill this board using these dominoes of shape, this like this? So this is the question, and the answer is no, because let's define R with a proposition such that this board has the same number of black and white squares. And so suppose that we can fill this board, we can basically tile this board using these dominoes. So we are trying to prove this proposition by contradiction, and we define R with the proposition that this board has the same number of black and white squares. And first, we can show that this R is true, and also this negation is true. So first of all, oh, sorry. we are going to show that R is true and negation of R is also true. So what is negation of R? So here R is saying that this board has the same number of black and white squares, meaning that negation of R means this board has different number of black and white squares. And this is true because if you look at this board has 32 black squares and 30 white squares. So this negation of R is true. But we also assume that we can tile this checkerboard using these dominoes. But if you put this domino on the checkerboard anywhere, you realize that this domino contains exactly one white square and exactly one black square. So if you use how many dominoes do you need? So there are 62 squares in this checkerboard. So you need basically 31 dominoes to tile this checkerboard. But if you use 31 dominoes, they have exactly 31 black squares and 31 white squares. So it should have the same number of black and white squares. So meaning that R is true. So we show that both R and negation of R is true. So that cannot happen, of course. So the meaning that the first assumption was false. So we cannot tile this board using this domino. Okay, and when you need to prove some proposition of the form like this, you can basically show both if P then Q and if Q then P separately, because these two propositions are logically equivalent. So showing this proposition is equivalent to showing this proposition and this proposition. So you can, so for example, here there's a theorem saying if n is an integer, then n is odd if and only if n squared is odd. So here P is the proposition n is odd, and Q is the proposition n squared is odd. And this theorem can be represented like this. So basically you need to show two propositions, if P then Q, and if Q then P. So you need to show that if n is odd, then n squared is also odd. And also if n squared is odd, then n is odd. And the first proposition can be, we can use a direct proof as we studied in the last class. It's easy to show. And when you show this this proposition, it is more convenient to show its contraposition instead. So you can assume that if n is not odd, meaning that if n is even, then you can show that n squared is even. So to conclude this theorem. Okay, and sometimes a theorem has the form of exist x, such that P of x. So this type of proof is called the existence proof. You just need to show that there exists an element x in the domain satisfying this proposition P of x. So there are two different types of proof. The first one is called the constructive proof, and the second proof is called the non-constructive proof. So in the first type of proof, in the constructive proof, you just basically look for an element. You basically find an element A such that P of A is true. So this is how you prove this statement. Here's an example. So here's a theorem is that the statement is that prove that there exists an integer that can be written as a sum of cubes of positive integers in two different ways. So meaning that there exists an integer n. This n should be written as a sum of a cube of positive integers. So there should be integers a and b satisfying this equation, but in two different ways. So there should be another pair c and d satisfying this. And proof can be done by simply showing that there exists an integer satisfying this property. And this integer 1729 can be represented as 10, the sum of 10 cubic and 9 cubic and 12 cubic and 1 cubic. And in fact, there's some related story about this theorem about some genius Indian number theorist Ramanujan. So there's he was born in India, but he moved to UK, and his supervisor Hardy and Ramanujan had some talk about this number, and Ramanujan actually found this property. Let me show you another strategy of proof. So suppose that there's a statement of the form like this. If P1 or Pn, then Q. So we can use the tautology that this proposition and this proposition are logically equivalent. So the reason is that in this proposition is basically saying that if n is to one of the propositions P1 to Pn is true, then Q is true. So meaning that if P1 is true, then Q1 should be true. And if Pn is true, then Q should be true. So these are two equivalent relations. And suppose that we would like to show the following theorem. Let A star B be max of A and B. So we define this operation as a maximum of two elements A and B. And in theorem, we want to show that A star B star C is equal to A star B star C for any A, B, C elements in the real number. So how can you show? So basically, we are showing that this maximum function satisfies the associativity law, and basically we can show this proposition by considering 6 different cases. So for example, first case is this, second case is this, and sixth case is like this. So there are, if you pick random 3 real numbers, they satisfy n is to one of these 6 inequalities. So in this case, A is the maximum value and C is the minimum value, and so on. So you can first show that n is to this one of these 6 inequality holds for any real numbers A, B, and C. And for each case, you can show that this equation is hold. So for example, in this case, if in the first case, this is A and this is also A. You can simply check these 6 cases and conclude the proof. But I think this non-constructive proof is sometimes more interesting. In this approach, you would like to show that there is an element A such that P of A is true, but you can show this statement even without finding such an element A. So here's one example. So in this theorem, we want to show that there exist irrational numbers x and y such that x to the power of y is a rational number. And this is how we prove this statement. So let's first consider the real number at the square root of 2 power of square root of 2. And we already proved that this square root of 2 is a rational number. So I assume this property. So if u is rational, so if we don't know if u is rational or not, but if u is rational, then we already proved this theorem because we can choose both. We can set both x and y as square root of 2, and square root of 2 to the square root of 2 is irrational. So we are done. But otherwise, if u is irrational, then square root of 2 power of u is 2. You can simply check this because u2 square root of 2 is this, this. So you can simply check this equation. So we know that u to the power of square root of 2 is 2, which is a rational number. So in this case, we can choose we can set x as u and set y as square root of 2. So since we know that y is an irrational number and we here assume that u is irrational, so we found the pair of x and y such that x to the power of y is a rational number. So what is showed here is that either this pair or this pair satisfy this property, but we don't know which one is a pair of irrational numbers. But we just proved that at least one pair, one of them satisfy this property. So yeah, so this is why this is called non-constructive proof, because we didn't really found the pair satisfying this condition, but we just used the indirect approach. So if you're wondering if u is actually rational or irrational number, you can use something more much more difficult theory in math, and actually u is an irrational number. So the fact is, okay, this is the end of section 1, and yeah, and we are going to move to the next lecture, basic structure. Any question? And before we move on, just in case you are interested in, so there are some interesting open source libraries which automatically find some proof for logical propositions. So there's one from Microsoft Research, for example. It's called Lean Prover, I believe. So you can just yeah, there's some very efficient programming such that if you give some premises and the conclusion that you want to prove, then this program automatically generates a proof for that premises and conclusion. So that's very interesting program, I think. I got one question in 60. Please make your question public. So I don't see any union or intersection here, but if you are mentioning this or and, then I believe this equation is true. And the next question was, is proof by cases is one of constructive proof? It's hard to say, but it's not. I mean, I think they are something like some orthogonal notions, meaning that you can still use both proof by cases and constructive proof at the same time, or you can use proof by cases and non-constructive proof. Okay. Okay, so today we are going to study some basic structures, including sets, functions, sequences, set cardinality, and matrices. I believe most of you are already very familiar with set and function or sequences. You should have studied them in high school, I believe. But by the way, I heard that nowadays standard high school education curriculum doesn't contain matrices, so students don't study matrices in high school. Is it true? I mean, is there anyone who never studied matrix in this room? No? Or wow, that's very unfortunate. Okay. I don't understand why matrix was excluded from the high school curriculum. That's weird. Okay, I understand. So, okay, let's begin from set. So, I am pretty sure that you're familiar with the set, but set is one of the basic building blocks for some types of object considered in discrete mathematics. And it is especially important for counting, or other programming languages also support these set variable types. And set theory is one of the most important branches in mathematics. And of course, we are not going to go deeply into this set theory. So if you're interested in set theory after taking this class, please consider taking some set theory class from math department. So there are many different system of axioms about set theory, and we are not concerned much about formal definition or formal set of axioms for set theory, but instead I will just use some naive set theory and based on some very elementary set of axioms. So here, in fact, even defining what a set is a very challenging issue. So it was one of the very actively discussed issue in math communities until 19th century. So I believe now mathematicians have a more well-defined notion of set or other related objects. But here I would simply say a set is unordered collection of objects, or this object are called elements or members of this set. But in fact, this is not the exact definition of set. So again, I'll ignore this part. And we use this notation to denote that an element A is contained in the set X, set A. And this is the negation of this proposition. And the elements of a set are listed usually between braces, like this. I'll show you some examples. So it is recall that when we studied the universal quantifiers and existential quantifiers, it was very important to determine the domain. So similarly here, universal set plays a very similar role in set theory. So this universal set contains some objects under our consideration. So we sometimes define universal set explicitly, or we sometimes implicitly use some set depending on from the context of our argument. So it's sometimes formally defined or not. And an empty set is denoted by this symbol. It is also called a null set. It's the set with no element, and a singleton is a set with exactly one element. So for example, this is a singleton containing just one element, 3. And we usually illustrate sets using Venn diagram. So the universal set U is often illustrated by this rectangle. And the set is usually represented as this circle. And elements of this set are usually represented as points. And here's a Russell's paradox, which is related to the definition of the set. So suppose that we can define the set S as the set of all sets, which are not members of themselves. So here U is the set of all sets, and S is a subset of this U, such that S X in U. We didn't study, we didn't define this symbol, but I use this anyway.